Welcome back, guys. It's time for another podcast of scientific computing. So this week we're doing TaylorSeries, and it's sort of an extension of what we did last time, but it's got a little bit of a more, how can I say, analytical twist. Let's look at it. Imagine we have a situation in which we have some fairly complicated function, but we're only really interested in the function in some small domain. And we'd like to find a quick, easy, approximate way to represent the function that's accurate as long as we stay within that domain. One approach to such a problem is to develop a series, a polynomial, that represents the function that is approximately equal to the function in that domain. And the kind of series we're going to study this time is called a Taylor series. So you've probably heard of Taylor series before. It's basically just a simple power series in powers of the distance from the point of interest. And notice that if the distance between a certain location and the point of interest is small, then the square of that distance is even smaller, and the cube is even smaller, and so on. So if you have a number that's tiny, squaring it makes it tinier, cubing it makes it tinier still, and so on. So the idea is if you don't get too far away, these successive terms in this series get smaller and smaller and smaller, and then the notion is that the series converges in some reasonable way. So let's look at that. The question is, how do I find these coefficients A, B, C, D, and so on? Well, the answer that the Taylor series is based on is that the function itself has a value. At the location of interest, the value of the function has to equal the value of the series at that same location. But the interesting thing is, if you put in x equals x0 into this expression, notice that the B term and the C term and the D term and all the higher order terms all go away, because at the location of interest, x0 in this case, the product of the B coefficient and the distance from the expansion point, x0, is 0. And all these higher order terms are also 0. And so you get the very simple answer that the function at the point of interest is equal to the A coefficient. The value of the function is the A coefficient. So that's it. We got our first coefficient. That was easy. Now let's look at the first derivative of the function. If I want to demand that the first derivative of the function be equal to the first derivative of the series, I have to take the derivative of the series. But of course the A coefficient goes away when you take the derivative because it's just constant. The B coefficient, on the other hand, survives because it gets multiplied by x. It's the first order coefficient. The C coefficient gets multiplied by 2 times the distance from the expansion point. And then when you plug x0 in for x, notice what happens. The C coefficient goes away, the D coefficient goes away, all the higher order coefficients go away, and you get that the B coefficient is nothing other than the first derivative. So there we have it, another coefficient. See, this is easy. Now you do the same thing with f double prime, and in that case the B coefficient goes away because you take the derivative of a constant and you get 0. The C coefficient ends up with a 2. The D coefficient is 6 times the distance from the point of interest, and so on. And when you put in x0 for x, the D coefficient goes away. Notice what's happening here. Every time we evaluate the function or its derivative at the point of interest, only one coefficient survives in the sum. It's the one that doesn't have any factor of x minus x0 to any power, but isn't 0 because it's been taken out by the derivative business. So you can see that in this case the D term goes away, and we get that C is the second derivative of the function evaluated at the point of interest divided by 2. I also want to point out that there's a factor of 6 in front of the D term, and if we did this again, we'd end up with D is equal to the third derivative of f divided by 6. And the 6 comes from having differentiated x minus x0 cubed 3 times. And what do you get when you do that? Well, you get 3 times 2 times 1. Well, you've seen that kind of pattern before. That's just n factorial. So in general, if you write this thing all out, what we get is that the Taylor series is nothing other than the nth derivative of f, evaluated at the point of interest, divided by n factorial, times x minus x0 to the nth. That's the general term. And so we can write the whole thing out using the summation notation as the sum of all n, the nth derivative of f, evaluated at the point of interest, divided by n factorial, times the distance from the point of interest to the nth power. And that's it. Okay? But what do we want to do it? What is the point? And the answer is, there are situations where this is a useful strategy for trying to analyze what's going on with the function. So I've cooked up a concrete example for you guys to study. There's a potential that's used in chemical physics that involves the interaction of 2 atoms in a diatomic molecule. In particular, this week we're going to study nitrogen. We're going to get data for the nitrogen molecule and identify what these parameters are. So there's 3 parameters in this model. The first is U sub m. That's the dissociation energy. That's how much energy does it take to tear these guys apart. It's sort of like the depth of the potential well. And x0, of course, is nothing other than the equilibrium separation between the 2 atoms. It's sort of like, where is the force between the 2 atoms? 0. And alpha is a measure of the sort of width of the potential. How wide is it? And how far do you have to move from the equilibrium position before the potential starts becoming significantly different from what it is at the equilibrium? The job we have is to estimate the frequency of oscillation of one of these nitrogen atoms in this well, in this potential well, that's produced by the interaction of it and its neighbor. And so what you're going to do is write a Python program that uses this potential. You basically compute a force from this potential and use the Hoyne method and Newton's second law to calculate how the atom moves in this potential that's produced by its interaction with the other atom in the diatomic molecule. And we're going to also use the Taylor series expansion to figure out what this potential looks like near the minimum, near the point of interest, and figure out analytically how should the thing move. And we're going to compare those 2 motions and the parameters of the model. So, how do we estimate that frequency? Well, we can start with the Taylor series expansion of the potential about the minimum. In order to do that, I want to introduce you to a new tool. It's called Simpi. Simpi is sort of like a Mathematica or a Maple, but it's built on Python and it's free, and you've already got it on your computer because it came with the software that we installed this semester. So let's see if we can use Simpi to figure out the Taylor series expansion of this potential. So I'm going to walk you through the notebook that I've prepared for this project, and we'll see how it works. Okay, so here is the notebook I've posted on ACE for you guys. It goes through a lot of the same math that's in these slides. In particular, I just described them, excuse me, the Morse potential, and this is about Simpi, the symbolic Python manipulator I was telling you about. So first thing you need to do is say from Simpi import star, and then I like to use the init printing function, which makes the formulas appear like mathematical formulas, kind of like the formulas we put in Markdown. And so I would recommend that. Now, the other thing I need to say is if you're going to try to mix Simpi and Pylab, you're going to run into trouble because they have a lot of the same names. And so if you want to do that, you're going to have to say, instead of from Simpi import star, you'll have to say import Simpi as sp. At least that's how I would do it. And then say from Pylab, no, say import Pylab as pl, The SP and the PL are just shorthand. You can make up whatever letters you like. But the point is, then when you refer to names within the PyLab library, you need to prefix them with PL. So if you wanted to plot, you'd say PL.plot. Or if you wanted a linspace, you'd say PL.linspace, and so on. And if you want to use a feature of Simpi, you'd say SP dot. For example, if you said import Simpi as SP here, you'd write SP dot init printing, open paren, close paren, to call the init printing function. So it's a little more typing, but you can, in fact, mix the two together. And there are tricks associated with that I can show you if you're interested. But most of the time, I'm either using Simpi or I'm using PyLab. I'm not often using them at the same time. So I guess the most common use case probably is if you want to make plots from symbolic expressions, then it's nice to invoke the PyLab. And then you have to sort of play that game. But anyway, onward and upward. Let's define the potential. First of all, we need to define all our symbols. So we have is the dissociation energy. X is our variable that tells us where we are. X0 is the variable, the parameter of the model that tells us where the minimum of the potential is, where's the equilibrium position. And alpha, of course, is the alpha parameter. And these are all going to be real. If you don't say real here, it will assume that they are potentially complex. And then when you go to find solutions, it can find complex roots. But today I'm only interested in the real roots of these equations. And so I want to tell Simpi that they're real. There you go. I'm going to go ahead and put in the expression for the Morse potential. And there it is. It looks a lot like Python. It is basically Python. Notice that I say U equals this stuff, and then on a line by all itself, I just say U. So this tells Python to print out the current definition of U, and it prints out this. Notice that it prints it out mathematically in a way that I can read, and that's really cool. So that's what the init printing function does for you. If you don't do init printing, it prints it out more or less in Python syntax, which that's okay too. So here's the real interesting part. I can ask it to take the derivative of U, to differentiate U with respect to X. And notice it differentiates it symbolically. I don't have to do this by hand. It does it symbolically for me. And then I can solve for the place where the derivative of U is equal to 0. So I just say solve UP for X, and it finds X0. So it discovered that the minimum, that there's an extremum at x0, and we happen to know it's a minimum because we saw the graph earlier. So that's sort of how you do it. You could also check the second derivative and see that it's positive there. In fact, let's do it. We'll go ahead and take the derivative of UP. UP was my shorthand for U prime, and U prime prime is the derivative of UP with respect to X. And notice it carries out all the algebra for me. I don't have to keep track of all that. That is so wonderful that it does that. And then the question is, what if I evaluate the second derivative at the location of the minimum? So the way you do that is you use the subs command, it means substitute. So evaluate UPP, but substitute for X, X0. And it figures out that if you plug in X equals X0, this is a 1, and this is a 1, and the whole thing boils down to 2um alpha squared. 2 times um times alpha squared. Um is a single number. It's the dissociation energy. And so what that means is that the second derivative U with respect to X is nothing other than 2 times the dissociation energy times alpha squared. But we also know that the second derivative of U with respect to X is nothing other than the effective spring constant. So we can use that to calculate the predicted period of oscillation. So that's it. First, obviously you're watching the podcast, so you see the podcast. But I want you to do two things, is to show that the experimental data is consistent with the Morse potential, and to use the Hoyne method to compute the period of a small classical oscillation of a nitrogen atom about the equilibrium in this potential. So that's basically all there is to it. There is one other little trick I'm sure you're going to hit. It turns out that if you've got two equal mass atoms connected to a spring, the point in the midpoint of the spring is the center of mass, and it's going to be at rest. So basically, it's as if both atoms are moving away from each other and toward each other at the same time, and so it's only half the spring that is engaged in the oscillation. And you remember that if you take a spring and cut it in half, the spring constant of the half is double. So the effective spring constant that you'd use to calculate the period is going to be double what you'd get if you just had a mass on a spring. You'd end up with double the spring constant. Or another way you could look at it is to use for the mass of the nitrogen atom half of its regular mass. That's called the reduced mass, and it's just a consequence of the fact that there's two masses actually oscillating about their common center of mass. So we can talk about that more in class. I thought I'd throw that in there here because it's going to come up sooner or later. So there you have it. Okay, so what we discovered was that you could expand the potential in a power series with a constant first term, that's the A coefficient, and then there was a second term that was the first derivative of the potential at the point of interest. Remember, where the point of interest was at the minimum of the potential. We'll talk about that more in a moment. Then U double prime has to do with the second derivative of the potential. That gives us the C coefficient, and then the third derivative of U at the point of interest, at the minimum, gives us the cubic term, and so on. We could keep going, but let's talk about what these different terms do physically and see how important they are. So the first term is a constant. It turns out that in a potential energy, a constant doesn't make any difference. If you have a constant potential energy, it produces no force. It doesn't affect the motion at all. It just adds or subtracts from the energy everywhere. So we can basically ignore that part. Now, the second term is the first derivative of the potential evaluated at the minimum, but you guys all know what the derivative of a function is at a minimum. In fact, we use the fact that the derivative at the minimum was 0 to solve for the location of the minimum. And so this second term is defined in a way. It's set up. We cooked it up to be 0. So that term doesn't do anything. I'm going to skip the quadratic term for a second and go to the cubic term. It turns out the cubic term is asymmetric, anti-symmetric about the minimum. That means that it's positive on one side of the minimum and negative on the other side of the minimum. It's what causes the potential not to be symmetric about the minimum. And so it's called the anharmonic term. It leads to non-simple harmonic motion. And the good news is, in our case, as long as the oscillation isn't very large, if the amplitude of the oscillation is not too big, this term is negligibly small. So for this project, we're going to neglect it. If you actually looked excuse me, if you actually excite nitrogen molecules significantly, this term is not insignificant, and you do have to take it into account. But for this week, we're going to neglect that, and that leaves this last term, and I call it the spring constant term, because let's look at it. It's a half times some constant. The constant happens to be the second derivative of the potential evaluated at the minimum, times the displacement from equilibrium squared. So it's 1/2 times a constant times the displacement from equilibrium squared. That should sound familiar. In fact, it should look just like the spring constant. It's 1/2 ks squared. S was the displacement from equilibrium. K is the spring constant. And so what we discover is that, in fact, the spring constant, the effective spring constant of this potential, is nothing other than the second derivative of the potential with respect to x. So very exciting. Well, how do we connect this with real data? So if you actually go out and look at the way nitrogen interacts with light, what you'll discover is that the dissociation energy, the depth of the potential, is about a little less than 7.4 electron volts. That the alpha parameter is about 2.3 per square angstrom. That the frequency with which the thing wiggles is a little less than 5.2 times 10 to the 13 hertz. think about that frequency. It's less than the frequency of visible light. It's infrared. So basically this is infrared electromagnetic radiation. And you actually don't need it for this project for the analytical part, but we're going to need it in order to simulate the motion because we've got to start the thing near equilibrium. The equilibrium position turns out to be about 1.2 angstroms. So when you start the thing moving, you might just start it out at 1.1 or 1.3, just a little bit from the equilibrium, and just let it go. And but you'll need this for your modeling in order to calculate the force and so on. So what I'm going to have you guys do is to, first of all, check that this data is internally consistent with the analytical model. So what you might do is use the parameters alpha, and x0 to compute the natural frequency and check to see that the natural frequency you get analytically with those model parameters matches the experimentally measured frequency. And then the other thing I want you to do is to put these parameters into the Morse potential, use Simpi to calculate the force function, or you can calculate it yourself just by hand, and then use that force and the Hoyne method to compute the motion of the atom in this potential well computationally, numerically, and see what the period of oscillation is, and thereby determine the frequency, and check that that frequency is consistent both with the analytical work you did using the TaylorSeries approximation and with the experimental frequency. And if all those things sort of match up, then you can have some confidence that the whole business kind of hangs together. It holds water. So that's the idea. We'll see you guys soon.